Okay? No?
Is the audio on?
Test, 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 test. No, it's muted. Test, test, test. Okay. Now here we go. It's online, I can start. Okay, so I hope you didn't have any problems at implementing this library. We will see the solution. And we can start from the variables, the internal variables that we decided to use. Actually, there is not really much to say. We also added a ramp step, which we will see later why it's used.
I wouldn't even explain it.
Okay. We will go directly on the CPP. The construction.
What is this clamp method that you have on top?
Okay, actually we added a clamp function for you to use, which is useful to limit a variable inside a specific range, a symmetrical range, and it's mostly used to bound the errors or other components of the PID, but mostly also for the velocity input that must be given to the motor. In fact, as you saw, the PVM library, the duty cycle function, takes an 8-bit integer, so a single byte integer, while the output of the control PID is a 2-byte integer. So if we don't bound this variable in a certain space, in a 1-byte space, we may actually overflow and obtain wrong values. I will skip the first function since they are quite easy, and we will go on the spin once function.
No, I would explain them all because they need it.
Okay. So I will describe all the functions. So first we have the use PID, which again is used to tell the class to use the PID controller, and we defined a simple flag, PID enable. Actually, these variables are defined are strictly defined on the header. Again, so you can pass to this function true or false actually, and this will then be used on the spin once function. Same can be said for the set speed function, in which we pass an integer, a signed integer, to the motor, and he will store it in its private space. Then for the spin method.
So one question. So actually the behavior of this module is that all set functions just set internal variables, and the actual work will happen only on the spin once.
Yeah, exactly.
Okay. So the class has a set of state variables inside. You don't do anything on the motor itself. You only write on these variables. These variables will then be read during at the interrupt time during spin once. In this way, you do not corrupt. You don't, because we have numbers like 16-bit numbers, and in this way, by doing this setting aside, you don't have that during that you write off an integer. You know what I mean? Like you just write down, you have your dashboard, you write there, and then there is another actor in your system that will read on the dashboard. Actually, if you want to be precise, we should use locks in the tool, right? Like when setting the variables, we should disable the interrupt and enable the interrupt once we have set the variables. We don't do this, but
for simplicity, but
to have atomic reads on this variable, because the AVR is an 8-bit CPU. So whenever we read the value which is larger than 8-bit, it's going to do multiple instructions. And each of these instructions can be preempted by potential emitter. If you're making a car, this is a sensible thing to think about. Otherwise, no. You write a 0 and then you write a large number, and then your car moves very quickly.
Okay, shall I repeat for
the false line.
Okay, so the main idea for our library is that we have a set of functions that we use to set up or give hints for the spin method, and we don't expect this function to do any work. since we concentrated all the work on the spin once function that runs in a synchronized way with the timer. Yeah, that's it. Yeah. So for the important function, again we first compute these the two encoder measurements, the one at the previous time iteration and the one at the current time. And with these two variables, we are able to compute our measurement speed that you can see here, and we also cast it to a signed integer, since we may be going in the other direction. Then I will first skip, assuming that PID is not enabled. We will just take the desired speed given in PVM space and output it for the motors in the later stages. While instead, if you use the PID, then we want to first store the previous error and compute the current one. Since, as you saw in the slides, we are working in discrete space, we require this type of computation. We then clamp the error, but you can skip this particular section. We don't need it in this moment. And then
clamping the error ensures that if the error is higher than the range, then the error is set to the range. If the error is lower of the range, so minus v, then it's set, so it's lower than minus v, then it's set to minus v. This prevents overshooting on the
output control.
On the output controller. So like if it goes out of bounds, you know already you limit it to the maximum, otherwise you would generate too much current in the system. Okay? And the same happens for the integral element, and this is so-called anti-wind up, which is a thing which is mounted on the integral term of the PID, because if you block the motor and then you issue speed, then the error is going to increase, and so the integral of the error. Then once you release the motor, you have a lot of error accumulated, which will result in a huge PID, and then when you release the motor will do boom, and then it will adjust. To prevent this effect, you limit the maximum integral coefficient which is accumulated by the PID with a window, by clamping the integral error to a maximum.
Yeah, exactly. And we have this anti-wind up installed here. So we are clamping actually the accumulation of integral error plus the current constant for integral term multiplied by the error, and we decided to clamp it to 255, even though we can also reduce this this term.
Clamping would work also without a flow.
Yeah. In theory, yeah. Just for we added it. Anyway. Then we finish computing the last terms for the PID, so the P term and the D term. And then we can actually compute the output of the PID by summing up all these three terms and clamping them to 255, just again to avoid underflowing or overflowing of variables. Once this result is computed, we can pass on the second part of the on the second part of the function, in which we go issue the command to the hardware itself. In this case, we first check the sign of the output PVM variable. In case it is negative, then we decide to control the motor on a given direction. So in this case, we set the direction A pin on an high value and the dir B to a low value. On the opposite case, we change the direction of the motor, and finally we pass the PVM signal, the absolute value of the PVM signal to the PVM module, which will then power up the real system. And this is it.
Yes. That wasn't impossible. I mean, actually, the nitty-bitty grit here is that there are a little bit of sugar, this clamping that we introduced and these sort of things. And these regimes, with these motors, we actually don't need it because we're not gonna break it, because the motor is much stronger than our fingers, so we will not manage to block it. Okay, so we will not need actually to clamp it, but this depends with these coefficients. This is something anyway that you tend to use. It was something even more. It's something that you tend to use once you do a real PID implementation. It's a little bit of experience aspects that prevent the system from misbehaving. Okay? There's a question in the lateral. I'm excited. Go ahead.
I was curious about the RAM step.
Ah.
In general overview, what's that?
Okay. Now, for a dynamic system, sometimes if you give it a step, what you will get is a response which is another step, but which is oscillating, right? What to have this is something you don't always want. So either you calibrate your PID very accurate, and so you could reduce the subrelongation effect, or alternatively, if you are a butcher, what you do is you say, I'm not going to give you a step as an output. I'm going to give you a ramp.
Okay.
And so this ramp is the maximum inclination of the ramp. So if you want to implement the ramp, you might. So the ramp means, given the actual PVM control, the next PVM control, and then you have a desired target, the desired PVM control that you want to reach, no? That will be the height of your step. But instead of reaching it immediately, you reach it by having increments that are at most a maximum that you define. So you are defining the slope of this ramp. So at each time, you say, where do I want to reach it? Oh, I want to go there. Should I go up or down? Up. Okay, if you should go up, then increase the actual PVM of that bit until you reach the value that you want to reach. And then, so you have this smooth effect.
And what's the benefit of doing
Stability.
That you don't have subrelongation effects, and then you don't stress that much the PVM. Because otherwise you might, if you observe the output of the PVM, you might have a banging up, down, up, down, up, down, up, down. Then what you lose is in the reactivity of the system, and what you gain is in the control that you send to the PVM. Otherwise, you might be also that you tell the motor go up, and then it's too much up, and then go down, and then you might have something that you don't want. You are more gentle with your electronics.
You get stability at the cost of response, actually, because of course by using this ramp you don't reach immediately the target you desire, but you have to wait a little bit more.
It's like an ABS brake, but
No. So your colleague is asking, is like an ABS brake? No, the ABS brake doesn't work this way. The ABS brake works that you have encoders attached to your machine. There's probably an IMU or something that's estimating the current velocity of the vehicle. And then when is it that you're skidding? When the predicted velocity, when the measured velocity of the wheels doesn't match with the velocity of the vehicle that you're predicting. Okay? And in this case, what happens is that if you're braking, if the ABS, once you press it, you get back on the pedal. It's releasing the brakes. By releasing the brakes, it enforces the wheel to get the natural grip and to get the speed of the stuff. Because the braking coefficient, once the tire is locked, then the tire tends to skid. It becomes more. So until you have grip, then you manage to hold something. Once you start sliding, now there is this effect that you might slide even further. The grip, yeah. It prevents you. It acts on you braking the ABS. Yes. What we can do it, but not on this robot. We might need an IMU, and then you can do the ABS, or you can do a traction control.
But the ramp, to conclude, the ramp is used mostly for stability reasons, without going too much into details, but at the cost of response time,
Yeah, okay. I would say that's enough. I mean, I hope that someone at home... I would say that that's enough. If for those of you that try to do the exercise, if not, I will stop this live. And meanwhile, that I set up myself, those of you that have done something can come here and try it on the board that we have on the back. Okay, meanwhile, I set up the lesson. So you stop the streaming and I start.
See ya.